In this lesson, we're going to discuss the derivative of order n of a function. Now, given a function f that is differentiable over its domain, the first derivative of the function f is denoted by f prime, which is the derivative of order 1, while the second derivative, which is the derivative of the first derivative, denoted by f double prime, is the derivative of order 2. As the third derivative, which is the derivative of the second derivative denoted by f triple prime, is the derivative of order 3. While the fourth derivative, which is the derivative of the third, is denoted by f to the 4. Now, the 4 at the exponent between parentheses actually denotes the derivative of order 4. So starting from the fourth order, this is how we denote the order of the derivative. And so on. We can keep on finding the derivatives of the function up to the order n, which is denoted by fn, the derivative of order n, where n is a natural number. Now, as a small remark, the derivative of order 0 is in fact the function itself, f. Looking at this example, we are given the function f of x equals to the cubic polynomial x cubed minus 3x plus 2. The first derivative, f prime of x, is 3x squared minus 3, while the second derivative is f double prime of x equals to 6x. The third derivative in that case would be equals to 6, and starting from the derivative of order 4, the derivatives of the function will all be equals to 0. So we can generalize this and say that the derivative of order n of x is equals to 0 for all n greater or equals to 4. However, it could be a little bit more complex than this. Looking at this function, for example, f of x equals to 1 over x. Now, I aim to find the derivative of order n, or an expression for the derivative of order n. And in order to do that, I need to start by finding the first 3 to 4 derivatives in order to be able to establish a pattern. So finding the first derivative of 1 over x. Now, we can refer to the derivative of the function in the form 1 over x to the k, which is negative k over x to the k plus 1. f of x is 1 over x. So over here, we can take k equals to 1. And applying that derivative rule for k equals to 1, I end up with f prime of x equals to negative 1 over x squared. Again, now 1 over x squared is also in the form 1 over x to the k, where k is equals to 2. So in order to find the second derivative, I apply the same derivative for k equals to 2. So I end up with f double prime of x equals to negative 1 that I had at the denominator of f prime of x times negative k, which in this case k is 2, so that's a negative 2 over x to the k plus 1, so it's x to the 2 plus 1, which is x cubed. Similarly, in order to find the third derivative, I also differentiate 1 over x cubed using the same derivative for k equals to 3. And then I end up with f triple prime equals to negative 1 times negative 2 times negative 3 over x to the 4. Again, the derivative of order 4, using the same derivative rule, I end up with the product of negative 1, negative 2, negative 3, and negative 4 at the numerator divided by x to the 5. Now, let's just stop here for a moment and see if we obtained a pattern that we can follow in order to deduce the derivative of order n. For f prime of x, n is in fact equals to 1. It's the derivative of the first order. So when n is equals to 1, I had at the numerator negative 1 to the power of 1, and at the denominator I have x squared, which we can see as x to the 1 plus 1. Now looking at the second derivative, the second derivative corresponds to n equals to 2 as it's the derivative of the second order. Now over here we have an x cubed at the denominator. The x cubed can in fact be seen as x to the 2 plus 1. And at the numerator, I have the product of negative 1 and negative 2. So I have two negatives here. So I can see that as if I have negative 1 squared times 1 times 2, and the 1 times 2 I can see as 2 factorial. While for the derivative of order 3, which corresponds to n equals to 3, I have x to the 4 at the denominator, which I can see as x to the 3 plus 1, and at the numerator I have three negatives, which I can see as negative 1 cubed, and the product of 1 times 2 times 3 we can in fact see as 3 factorial. Now similarly for n equals to 4 and the derivative of order 4, we have as well negative 1 to the 4 times 4 factorial divided by x to the 4 plus 1. So we can in fact see a pattern here. So for the derivative of order n of x, we have in fact at the numerator negative 1 to the n times n factorial and divided by x to the n plus 1, and that works for all natural numbers n. Now that we have deduced a pattern for the derivative of order n, in order to confirm that this is really the derivative of order n of the given function, I'd have to in fact prove it by induction. So in order to prove by induction that the obtained expression is the derivative of order n of the given function, I start first by checking if that rule works for n equals to 0 for the first value of n. And as n is a natural number, the first value of n is in fact 0. So replacing n by 0 in the obtained expression, I get negative 1 to the 0 times 0 factorial divided by x to the 0 plus 1. Now negative 1 to the 0 is 1 and 0 factorial is 1. And at the denominator, x to the 0 plus 1 is x, which leads back to f of x. And we have seen already that the derivative of order 0 is the function itself. So this is confirmed for n equals to 0 for the first value of n. However, next I assume that the statement is true for n, which means that up to rank n, we have the derivative of order n to be negative 1 to the n times n factorial over x to the n plus 1. And next, I need to prove the statement true for the next rank, which is n plus 1, which means that I need to prove that the derivative of order n plus 1 is negative 1 to the n plus 1 times n plus 1 factorial over x to the n plus 2. So I start by the fact that the derivative of order n plus 1 is the derivative of order n. So I am in fact here using my assumption as this is a proof by induction. So differentiating the derivative of order n using the same rule I've used before, 1 over x to the k, its derivative is negative k over x to the k plus 1, I have in fact negative into n plus 1 times negative 1 to the n times n factorial divided by x to the n plus 2. The negative into n plus 1 comes from the exponent of the denominator of the derivative of order n. And then I increase the exponent of the denominator by 1. Now rearranging the numerator, the negative times negative 1 to the n would in fact be negative 1 to the n plus 1. And the n factorial times n plus 1, as n plus 1 is the term that comes right after n, the product of n factorial and n plus 1 is in fact n plus 1 factorial. Consequently, I deduce that it is true for n plus 1, and therefore that expression I obtained is in fact the derivative of order n of the given function.